Now this part of thermodynamics, we are looking at the fundamental heat transfer. So basically, heat transfer consists of conductions, convection, and radiation. But in our fundamental heat transfer, we'll be only looking at conduction and convection. So sorry, there's a little bit of lag here. The transfer of heat, can take place by two phenomena known as conduction and radiation. Now, this phenomenon may take place in a given system, that is a working fluid that we are referring to, on their own, or they may occur simultaneously. As a result, conduction or radiation occurring into a fluid media, then a transport of heat may occur, which is known as convection. So the first part here is conduction. So the transfer of heat by conduction is found to depend upon the following factors below. So it relies, or it is a function of all these factors that I've listed down here. First one, the area to which heat transfer takes place. Actually, the greater the area, the greater will be the amount of heat transfer, or the rate of heat transfer will be higher. The smaller the area, the rate of heat transfer will be taking a longer time. It will take a longer time or lower. Second, the temperature difference of the phases through which the heat is passing. The temperature difference. So here is the temperature difference. So the greater the temperature difference, the greater will be the heat transfer rate. The smaller the temperature difference, the heat transfer rate will be lower. Then third, the time taken for the heat transfer. This is definitely the longer the time, the greater will be the heat transfer. So conduction, heat transfer by conduction is actually directly proportional to the area, the temperature difference, and the time taken for the heat transfer to take place. Then the fourth one is the thickness of the material. The slimmer, or that means the thinner the material, the easier that the heat is being transferred through the wall of the object. So the thickness of material through which the heat is passing, is transferred. So remember, thicker the material, time taken for the heat to pass through the wall will be longer. Thinner the material, then the heat transfer passing through the wall will be shorter. So that means that heat transfer by conduction is inverse proportional to thickness of material. And of course, the type of material. For example, copper, steel, gold, and etc. So different materials will give you a different amount of heat transfer rate. So, and the type of material that we are referring usually is shown in, or each material will have a different thermal conductivity, a different value of thermal conductivity, and it is denoted by the symbol of lowercase letter k here in these notes here. So this is an example of the heat transfer by conduction. So the matter, the atoms of metals, usually it is closed packed. So when heat is transferred to the atoms, it will be distributed through or to its neighboring atoms or neighboring particles, and that is through the vibration of each individual particle or atom. So that is how heat is being transferred by conduction. Okay, atoms are energized and vibration increases. Now, the greater the area and temperature difference, the greater will be the heat transfer. The heat transfer is therefore proportional to the area and the temperature difference. 2. The greater the thickness of material, the smaller the heat transfer. The heat transfer therefore is inversely proportional to the thickness or the wall thickness. Now consider a flat plate. Now this first part here we are looking at heat transfer through flat surface or walls. Okay, so let us have a flat plate or wall of thickness x and the heat transfer rate area, the heat transfer area to be A, thickness to be x, heat transfer area to be A, and the temperature difference of its phases be T1 and T2. So here, Q dot here, it is actually referring to the rate of heat transfer proportional to the area, through which the heat is penetrating through, and then this is the difference in temperature, and this is the thickness. So as we convert this to an equal sign, then you can see there is a constant K here, and this constant K here is actually the thermal conductivity. It's a constant, it's a material constant. So delta T can be referred as T2 minus T1, that is the temperature difference between the inner surface and the outer surface. Which temperature is greater? It depends on whether the inner surface is having a higher temperature than the outer surface, or in the case if, let's say for example, the outer surface is having higher temperature than the inner surface of the material. So X is actually the thickness of the material. So K is the constant of proportionality, and it is known as the coefficient of thermal conductivity. K is known as the coefficient of thermal conductivity. Excuse. So the K value here, it varies with respect to the materials that we have. So for example, gold and copper, definitely the coefficient of thermal conductivity for gold is higher than for copper or for steel. So therefore the heat transfer will be greater for any materials that is having a higher value of coefficient of thermal conductivity. So here I have a diagram. So this is the area. So this is only a 2D. If it is a 3D, you can see, that is actually the heat is penetrating through a wall, with a width and a height here. So area which is perpendicular to the flow of heat. So the direction of flow here is actually perpendicular to the area at which the heat is penetrating through. Now from T1 to T2, as you can see, it is hot, so we have T1 which is at higher temperature region, and T2 which is cold, a colder surface, or the outer surface which is at lower temperature. So the difference in this will give you a temperature gradient. So, and this represents the thickness of the wall, and K of course refers to the material that we use for the wall. Let's say concrete, and then timber, then of course the K, the thermal conductivity, the coefficient of thermal conductivity for both the concrete and the wall, concrete wall and a timber wall will be different. So the first part is the conduction through composite walls. Composite walls means maybe you have walls that is made up of layer of different materials. So the heat that is penetrating through each layer will be different. The rate of heat transfer will be the same, but then the heat that is penetrating through the different material is actually slightly different. So here we have 3 layers. I have 3 different materials with respect to K1, K, remember, is the coefficient of thermal conductivity. So we have K1, K2, and K3. So 3 different materials and having thickness of X1, X2, and X3. So the heat will be penetrating or passing through the wall of this, okay, material. So let's say this is the heat, okay. So you have it penetrating through the first layer of the wall, then to the second layer, and then through the third layer. Okay, so there will be definitely a temperature drop across the layers. Okay, T3 and to T4. Okay, now Q dot are passing through the wall. That means the heat transfer rate. The Q dot is actually the heat transfer rate, and it is measured in watts respect to time. So remember we have this formula earlier, okay? Q dot is equals to K1, the coefficient of thermal conductivity through the first layer of the wall, and then the area of course. So for example, in this case, the area should be the same throughout all the 3 layers, and T1 minus T2 is actually the temperature difference, okay? So X1 is the thickness of the first layer here of the wall. So K is coefficient of thermal conductivity, A is the area, and then T1 minus T2 is the temperature difference, X1 is the thickness of the first layer, and Q dot is the rate of heat transfer through the first layer. Okay, so manipulating this equation, we will have T1 minus T2 equals to Q dot X1 over K1 times A. A is the area, and Q dot and then for this is the Q dot for the second layer. Okay, the Q dot actually, which is the heat transfer rate, should be constant throughout the 3 layers. The only thing is the temperature difference. It drops slightly or it drops more. It depends on the type of material. Okay, so you have the third layer, the Q dot for the third layer. So transposing equation above, means manipulating this. So that is T1 minus T2, and this is for T2 minus T3, this is for T3 minus T4, and then you add up all these 3 equations here. It forms the final equation, that is this here. Okay. So that's all for this section. Okay, hope you understand what I have explained. If you are unable to understand or if you have any comments, please put on the space below in my YouTube channel. Okay, in the comment section below. You can put a like or subscribe if you like my video. Thank you. I will be continuing with the part 2, that is through a cylindrical wall, that is heat transfer flow through pipes or cylindrical wall, thin and thick cylindrical wall. Thank you. Thanks a lot for the viewing. Thanks. Bye bye.